Today we will discuss tetrahedral and octahedral voids. Already we mentioned voids are the vacant spaces in a crystal lattice. There are two types of voids. First one is tetrahedral void. A tetrahedral void formed between four spheres. A tetrahedral void is formed when the centers of the four spheres are joined. When the centers of the four spheres are joined, we will get a tetrahedron, therefore the name tetrahedral void. So here you can see the figure of tetrahedral void. These three are the spheres of one layer, and it is the sphere of the upper layer. So when this sphere comes over these three, you can see it here. A tetrahedral void will form. When you join the centers of these four spheres, a tetrahedron is formed. So in solids, in the case of HCP and CCP, we can identify tetrahedral voids. And if there are n spheres, there are 2n tetrahedral voids. So what are the important points related to tetrahedral voids? Voids formed in between four spheres. When you join the centers of the four spheres, a tetrahedron is formed. And if there are n spheres in a crystal lattice, 2n tetrahedral voids are present. N spheres means n particles, the total number of particles. For example, if you consider face-centered cubic crystal, FCC crystal, a unit cell, face-centered cubic unit cell, you know the total number of particles 4. So how many tetrahedral voids will be present? 4 tetrahedral void, 4 into 2, that is 8 tetrahedral voids will be present. In a face-centered cubic unit cell, total number of particles 4, therefore 8 tetrahedral voids are present. Now the second type, that is octahedral void. Octahedral voids are formed in between 6 spheres, 3 spheres of one layer and 3 spheres of the other layer. When you place these 3 spheres over the 3 spheres of the first layer, in between them, an octahedral hole is formed. As we already mentioned, it is extending the first layer and reaching here in the second layer. So it is continuous in first and second layers. When you join the centers of these 6 spheres, you will get an octahedron. Therefore, the name octahedral void. If there are n spheres in the crystal lattice, there will be n octahedral voids. Spheres means particle. N particles in the crystal lattice, there will be n octahedral void. For example, in FCC unit cell, face-centered cubic unit cell, 4 particles are present. If there are 4 particles, how many octahedral voids are present? 4 octahedral voids. But how many tetrahedral voids? 8 tetrahedral voids. How many octahedral voids? 4 octahedral voids. So we can say voids formed in between 6 spheres, that is octahedral void. When you join the centers of the 6 spheres, you will get an octahedron. If there are n spheres in a crystal lattice, Then there are n octahedral voids, number of spheres or particles equal to number of octahedral voids. Where is the position? We mentioned in FCC there are 4 octahedral voids and 8 tetrahedral voids. Where is it present? Or the position of tetrahedral and octahedral voids? Or the location of these voids? Where is it? First, we can see the location of tetrahedral voids. It is a face-centered cubic unit cell, FCC. You can see particles are present in all the corners and particles are present at the face enders. It is upper face, one particle is present here. Right side, one particle is present here. Bottom, one particle is present here. Left side, particle is present here. Front, one particle is present here. Back side, one particle is present here. So it is a face-centered cubic unit cell. And you can see it is divided into 8 portions. And you consider this one, you consider the first square. It is one square, it is another square, and they joined, you will get a cube. So we can consider it as the first cube, second cube, third, fourth, fifth, sixth, seventh, eighth. Eighth cubes, we can divide it into 8 cubes. And in each cube, how many spheres are present? 1, 2, 3, 4. Not this one, this one. 1, 2, 3, 4. 4 spheres are present. This sphere belongs to the cube behind this one. You cannot count it. 1, 2, 3, 4. When you join the centers of these spheres, you are getting a tetrahedron, and that is a tetrahedral void. So from this figure, it is very clear there are 8 tetrahedral voids in FCC. What is the total number of particles? 4. How many tetrahedral voids? 4 into 2, 8. So 1, similarly here 2, 3, 4, 5, 6, 7, 8. 8 tetrahedral voids are present. The voids formed between 4 spheres. Here, if you consider this one, 1, 2, 3, 4. Top, 1, 2, 3, 4. It is the position of tetrahedral void. Now, where is the position of octahedral void? Again, you can see it is a face-centered cubic unit cell. Here, at the body center, there is nothing. No sphere at the body center. And it is the front face. One particle is present here in the middle. It is the back face. One particle is present there. It is the right side. One particle is present here. Left side face. One particle is present here. It is the upper face. One particle is present there. Bottom face. One particle is present here. Total how many? 1, 2, 3, 4, 5, 6. 6 spheres. In between 6 spheres, you can see a free space, and that free space is known as octahedral void. So where is the position of the octahedral void? It is at the face center. We can identify, sorry, not at the face center, body center. We can identify the octahedral void is present at the body center of FCC. But we told there are 4 octahedral voids in FCC. One is at the body center, then where is the remaining? One is shown here. Here, this position. Now particle is present there, this position, can be considered as an octahedral void. So at the body center, one is present, and in this position, another is present, 2. Here, another one, 3. And here, in this side, there is one more present, 4. So total 4 octahedral voids are present. But we can identify the octahedral voids are not limited in one unit cell, that is extending to the adjacent unit cell. That is why this particle not belongs to this unit cell, that is extending to the adjacent unit cell. Therefore, this octahedral void is not completely belongs to this unit cell. Here one particle is taken from another unit cell, here one particle is taken from another unit cell. So actually it is shared by more number of unit cells. So we can identify all these vacant sites represents an octahedral void. Effective number of octahedral void will be 4. At the body center, one octahedral void is present, and that is completely belongs to this unit cell. But in all the edge centers are free. In all the edge centers, there are octahedral voids, but that octahedral voids are not belongs to one unit cell, but that is shared by 4 unit cells. Edge center will be shared by 4 unit cells. So effective number will be 4. Now based on this, we can solve some problems. You read the first problem. Atoms of element B form HCP lattice, and those of the element A occupy 2/3 of the tetrahedral voids. What is the formula of the compound formed by these elements A and B? I will explain this one. Atoms of element B forms HCP. B forms HCP. That means B forms close-packed arrangement. Therefore, A will be present in the voids. Here it is clearly given A occupy 2/3 of tetrahedral voids. For example, you consider there is one B particle. Then how many tetrahedral voids will be present? 2 tetrahedral void will be present. All the tetrahedral voids are not occupied by A. Only 2/3 is occupied. So out of these 2 tetrahedral voids, 2/3 only occupied. So what will be the formula? B will be the anion. If it is forming voids are small, so A will be the cation. So first we have to write A. A 2/3 B. A, if there are one particle, then how many octahedral voids will be present? 2 octahedral voids will be present. But here what is the problem? The 2 octahedral voids are not half of the tetrahedral voids. If one particle is present, 2 tetrahedral voids are present. If there are 2 tetrahedral voids, there should be 2 cations to occupy, but in this case, this is a special case, only 2/3 of tetrahedral voids are occupied. So total number of voids 2 into 2/3. So how many A particles are present? 2 into 2/3, 4/3 is present. So we can write the formula as A 4 by 3B. But fractions are not allowed. So in order to make complete numbers, you have to multiply 2 to 3. A 4 by 3 into 3, A4. B also you have to multiply with 3. So B3. A4, B3 will be the answer. Similarly, you can find out the answers for the second and third questions. I will give it to you as an assignment. Solve it and submit. Okay. We can stop it here. Next day, we can discuss the packing efficiency.